Okay, the concept of a sampling distribution and the central limit theorem, like it says up here, is kind of paramount to everything that we do the rest of the way in this course is really true. So I want to begin to try to unpack it with hopefully a familiar example that we've looked at in the past. If I roll a single six-sided die, right, and I do that many times, right, these are possible outcomes. I could land on a 1, a 2, a 3, or 4. And we know if we average those outcomes in the long run, the expected outcome or the average outcome is a 3.5. We know we can't ever roll a die and roll a 3.5. It doesn't happen, but that's our average. And then this is the standard deviation. This means, on average, how far these numbers are consistently over time from the average of 3.5. That's what we mean by spread. So we have the center, we have the spread, and then the shape is uniform, right? All of these outcomes are equally likely, 1, 6, 1, 6, 1, 6. Okay? Think of doing that infinitely many times. That's what that distribution will look like. Now, we're going to change our sample size to 2, but we're going to take a sample mean. All right? This is a little bit different than what we did in Chapter 6. If you're thinking in Chapter 6, well, why is the spread smaller? If you were thinking, if we roll 2 dice, shouldn't we add the variances? And that would be true if we were adding the results. It's not what we're doing. We're going to average them. Okay, we're taking a sample mean. So when I roll 2 dice and I get a 1 both times, right, the average would be a 1. Well, how often can that happen? Only 1 out of 36 times, right? I roll a 1 and a 1, and there's 36 different ways I can roll the 2 dice. If you think of that spreadsheet, there's only one way to roll a 1. There's only one way to roll an average of a 6, right? So this is an average of 1. It means that I took the 2 dice, they were both a 6, and I averaged them. The 5.5, that would come from rolling a 5 and a 6, or rolling a 6 and a 5. So there's 2 out of 36 ways that can happen, and so on. So hopefully what you notice right away in terms of similarities and differences between these two distributions, the biggest similarity is that the center is still the same. Okay, the average of all these sample means is still 3.5. That doesn't change. What happened to the spread? We will have a rule for that. I'll show you how that it changes. But in general, for now, we should notice that it got smaller. Right? It did have a standard deviation of 1.708. Now it's 1.207. And then the second big difference that we ought to notice right away is the shape. It went from being uniform to being this would be unimodal, right? Mound-shaped and symmetric. So this is still symmetric, right? But it didn't have any kind of mound shape. It wasn't unimodal. Now we have this mound shape. It starts to take on that normal shape. And if we were to roll 3 dice and average them, guess what would happen? This would still live in the middle, but the spread would start to decrease and it would become even more pronounced as a normal shape distribution. So big takeaways there, just starting on a small scale. This is what we're doing today. If I take the average of these outcomes and I keep averaging them, the center stays the same. It's the same as the population center. The spread gets smaller as the sample size increases, and then the shape will get more symmetric as sample size increases. So let's look at some computer lab simulations and unpack this a little bit more. So you can find a copy of this worksheet in our Schoology page. But the big thing I want to do here is get to this website that I have listed up at the top here. Okay, so that link up at the top there takes you to this online stat book and a really helpful website that we'll be using where it simulates a sampling distribution. It's a little bit more, one of the more, I think, abstract concepts for us to try to wrap our heads around. So we're going to start sampling from a normal distribution. If you look at the worksheet here, our parent population in the beginning here is going to be a normal distribution. So we shouldn't be surprised as what's going to happen when we sample from a normal distribution. But then in our second task, we're going to do the same thing, but we're going to sample from a skewed right distribution, and we'll try to observe what happens in that situation. And then we're going to make up our own distribution, our own shape, and we're able to do that with this with the simulator. And otherwise, this would be kind of hard to try to picture a lot of what's going to be happening here. So when I go to this population here, I want to make it clear what's happening. I'm going to go into this population and sort of like what we did, oops, it's clear. Sort of like what we did in the beginning there with rolling 2 dice. I'm going to take 2 numbers from this population, okay? and I'm going to sample them 2 at a time and average them. And then what I'm going to do is I'm going to plot the averages. That's what you're going to see happening down here. So I'm sampling for the mean, and then when I click here and I click animate, it takes 2 numbers and then average them, right? So this was just my sample of 2 numbers from this population. It's a small sample size, but what we did was we averaged them and then plot the average down here. I'm going to do it again. 2 numbers, average them. Okay. What's being populated in blue, the concept down there is what we call a sampling distribution. It's a distribution of sample means. So we're getting all these averages and plotting the averages. Okay, so I like to animate it at first so you can see what's happening here. I take 2 numbers, I average them, and then I plot the average. Okay, so now to speed up the process, because the sampling distribution truly would be all positive averages, every single possible combination of 2 numbers that I can get here, and average them and plot them. That's what we mean by the sampling distribution. So I'm going to do this, taking 2 numbers and average them. I'm going to do it 100,000 times with 1 click of the mouse. Ready? So what do we notice in this sampling distribution when we think of the center, the shape, and the spread? So if we look at the parent population, the mean was 16 and the standard deviation was 5. So I'm going to write that down. Okay, I started with a mean of 16 and a standard deviation of 5. When I sampled 2 at a time, what happened? Well, it looks like the mean is still 15.98. It's still about 16 if we round that. But now the standard deviation's gotten smaller. It's 3.54. Okay, and the mean was still about 16. The shape is still normal. So we notice right away, just taking 2 at a time, our standard deviation, our spread, is getting smaller. Okay, now I'm going to change the sample size. Notice here, I can change my sample size. I'm going to change it to 5. I'm going to take 5 numbers at a time, and we're going to animate them. Right, and so this blue dot is the average of these 5 numbers. And there's another average. Right? So you can see the more numbers we get, we get a wider variety of numbers to contribute to our sample, but you're going to start to notice that the sample mean becomes a more precise estimate of the actual population mean. So I'm going to go ahead and, again, with a 1 click of the mouse, I'm going to do that 100,000 times. Okay, so the mean is still 15.99. It's still very, very close to the population mean, but standard deviation, again, keeps getting smaller, 2.24. And still normal. Okay. And then I'm just going to continue to do this. Let's change the sample size to 10 and see what happens. Again, if you need to, you can see what's really happening here is we're going to take 10 numbers from there. We're going to average them, and it would take a really long time if we kept doing that 10 numbers at a time. So to speed up the process, I click the 100,000 button and do it all in one shot. So my mean is 16. The mean of all these samples mean is a 16.01 or 16. And now the standard deviation is all the way down to 1.58. So you'll notice a trend here. The sample mean, or the mean of the sample means, is still the population mean. It doesn't change. And you're going to notice that the shape continues to be normal. It just, the peak that's in the middle kind of becomes more pronounced, taller, because there's less variability. This standard deviation number just keeps getting smaller and smaller and smaller. So now if we change this to 16 and do it 100,000 times, we notice the standard deviation keeps shrinking, 1.25 now. Okay. And I'll explain the rule for what's happening with that standard deviation when we get to the end of the lesson here this morning. Oops, I didn't really want to grab all 20 of those, but again, it's taking 20 at a time, and then I'm going to get a little blue point that is the average of this 20. So we do that 100,000 times. Our standard deviation is 1.12. And now finally, let's do it. Sample size is 25, and I'll also do that 100,000 times. 16, and now the standard deviation is 1. Okay, so what's really happening to the standard deviation each time? The standard deviation of the sample means, I call that sigma x bar. It's the population standard deviation divided by the square root of n. Okay, and you'll notice that formula is on your formula sheet. So we don't ever have to commit that formula to memory, but you'll notice here as we get into inferential statistics and sampling, you'll see the formula that I just pointed out to you when we're dealing with population means. We'll deal with proportions, but for population means, it's right here. Sigma x bar is the population standard deviation divided by the square root of n. And we generally will use the sample standard deviation. But here, for our intents and purposes, as we're exploring this the first time through, try to keep that in mind. And we'll, you can test it. You can see it's 3.54. It's 5 divided by root 2. This is 5 divided by root 5. Okay, and you can really see it here in this last one because the population standard deviation was 5, and what's 5 divided by the square root of 25? It would be indeed 1. So it came out pretty close to following that rule. In fact, exactly following that rule. So now what's going to happen if we make the original population skew to the right? Let me show you what I mean. So here we're going to go to the parent population and clear this. And you can see we can change the original population to uniform, like rolling a six-sided die like we did. And you saw that. I mean, this is our example in the warm-up. If I take 2 of these at a time and then start to average them, and I do that a bunch of times, look, we get a mound in the middle, just like we did with the dice. So I want to start with a skewed distribution because if we only take 2 numbers at a time from a skewed distribution, you're going to notice, and I'll do that 100,000 times, the sampling distribution is still kind of skewed, but it's a little bit less skewed, right? So the mean is going to be 16 still. Oops. We're going to stay with a mean of 16, I believe. And I think, let me just double check on that standard deviation. The standard deviation is 6.22 to start with. Oh yeah, and the mean is 8.08. Okay, so we have a mean of 8.08. And a standard deviation of 6.22. That's for the population to start skewed right. Okay, it's not bound, shaped, and symmetric. And when we took 2 at a time and averaged them, the mean was still close to 8.08. It's 8.07, and the standard deviation is 4.39. This is still pretty close to the population mean. It's not really changing, and it's less skewed, but it's still skewed, but less so. Okay, and now let's go back again. Now we'll change the sample size to 5. Take 5 at a time. So we're taking 5 numbers. Remember, we're going to average them and then plot the averages. I'm going to do that 100,000 times. Now I can still see a little bit of a skew, right? I can see that the mean is a little bit bigger than the median, 8.09 compared to 8. And the standard deviation continues to get smaller. That's 2.77. And I'll bet if you take 6.72 and divide it by the square root of 5, it is probably pretty close to that 2.77 number. And this is still 8.08. The mean of the sampling distribution should equal that, and it becomes even less skewed. Almost normal, right? Getting real close to a normal mound shape. So now what happens when we increase that sample size to 10? Right, so we do that 100,000 times, pretty much close to normal. Mean is 8.08, standard deviation is 1.97. So what we're seeing here is that once our sample size gets significantly large, and you'll see if I just fast forward to the end of this little worksheet here, let's go all the way to 25. When I get a sufficiently large sample of, let's say, 25, and remember, I'm going to keep doing this over and over and over and over again. Now look at the sample of 25. Look at this little sample. It kind of resembles the population, right? If I looked at this sample of 25 numbers, I can see it's kind of skewed to the right. But then when I average those 25 numbers, it starts to take that skewness away. And if we go ahead and do that 100,000 times, it's pretty much a normal shape distribution. So these are the big parts of the central limit theorem. We need to be able to articulate what happens to the center of a sampling distribution, what happens to the spread, and what happens to the shape. And this is huge for us, right? Because it tells us if our sample size is large enough, then we can assume that we have a normal shaped sampling distribution, which means all of our normal CDF calculations will be in play, and we will be able to predict pretty accurately how we ought to expect outcomes to behave. So now back to a new population here, what I like to do in this case is we can make a custom, and what I try to do is call this the anti-normal. So what happens here is I have peaks on either side, right? This is the exact opposite of a normal distribution. But I have a mean of 16.26 and a standard deviation of 12.39. That's what that was, right? 16.26 and a really large standard deviation, right? 12.39. Most of the observations aren't anywhere near the center, right? The center is 16, but most of the observations are really far from it. So let's see what happens in this situation if we take 2 at a time, right? If we take 2 at a time, it's going to start to resemble the parent, but notice what can happen sometimes here, like you just did there. I could get a point over here to the right and a point over to the left, and a lot of times that's going to happen. And when I average them, well, where's that average going to be? It's going to live right in the middle, okay? So what happens if we do this 100,000 times? You automatically start to lose the peaks in the tails and start to get a peak in the middle, all right? So how would I describe that shape? Let's see, what was our mean is still the same, 16.25. Standard deviation is getting smaller. This is still 16.25 roughly, 16.26, that's not changing. And then we start to get a small peak in the middle. Right? And also smaller tails. Those two tails where they started being the highest points in the distribution, they're starting to shrink. So what happens if we do 5 at a time? Okay, I'm going to take 5 at a time. So we take 5 numbers and average them. So hopefully you're getting a good idea of what the central limit theorem is all about. And then by the time I get to a really large sample, watch what happens. We have a completely non-normal population, but it's not going to matter if I take 25 numbers from that really non-normal distribution and plot the sample means, we get a normal distribution. This is the big takeaway for us. It's extremely important. So the central limit theorem, the conjecture, it's not a conjecture, it is the central limit theorem. I will spell it out for you here. Okay, as it relates to center, I'll use some symbols. Okay, when we talk about center, this means that the mean of the sampling distribution, the mean of all the x bars, is equal to the mean of the population. Okay, so it's really important that we, look and focus on what we're talking about here. This is the mean of the x bars. This is the mean of the population, mean of x, but they are equal to each other. When we're talking about the spread, generally we're going to use standard deviation. The standard deviation of all of those sample means of x bar equals the population standard deviation divided by the square root of the sample size. It keeps getting smaller. Okay, so that's the second takeaway. We have 3 pieces to the central limit theorem. We want to talk about the center, talk about the spread, and then finally the shape. And we have here, if n is large, the shape will be approximately normal. But we also have a case where n might not be large, right? If n is small, then the shape will resemble the population shape. So if n is a smaller number, like n equals 2 or n equals 5, the sampling distribution will resemble the population shape. Okay, so those are the big 3 things for the central limit theorem, how they apply. Now, what we are going to be doing is applying them in two situations, basically. Okay, we are going to be talking about using this for proportions and for means. We want to estimate means and estimate proportions. So the whole purpose of this course is to estimate our population parameters, okay, using sample statistics. So easy way to remember this is keep your S words together. If something is talking about a sample that you gathered, that you collected, then that's a statistic. It's a sample statistic. So when we estimate a mean, we use mu, population mean. When we're talking about a sample statistic, to estimate that, we use X bar, okay? When we estimate a proportion, we use P, okay? Your textbook authors use P. Sometimes you'll see textbooks that stay with the Greek and use pi, okay? For our sample statistic for a proportion, and if you've been in my classroom, somebody asked me this, I think, early in the year, what are all these P's with the hats on them? That's P hat. That's a sample proportion. It differentiates between. It means that I took a sample of 50 people and said, what proportion of you are going to vote for so-and-so in the election, okay? So for standard deviation, again, we've seen this symbol often, sigma, and for sample standard deviation, we just use S sub x, okay? That's your sample standard deviation. This would be sigma sub x, okay? So generally, when you think about it, these are going to be all unknown. We don't really know what these are. We're going to, a lot of times in the beginning here, as we try to study sampling distributions and understand the concept, we will say, assume we know that it equals, such and such, but these are really unknown parameters. And we use sample statistics to estimate them.